Welcome to example number 12. We have a long straight wire and a circular loop wire. The long straight wire carries a current of 8 amps and the circular loop wire carries a current of 2 amps and a radius of 0.3 meters from here, and the other wire is assumed to be also a distance of 0.3 meters away. We're asked to find the magnitude and the direction of the net magnetic field at this point C, which is the center of the loop. Let's first examine what the magnetic field lines would look like around these two wires. So if we were to consider the long, straight conducting wire right here, we'd use the right-hand rule. So applying the right-hand rule for the long, straight conducting wire, we would orient our thumb in the direction downwards as if you're holding this wire and your thumb is pointing in that direction of the current. And your fingers will curl in the direction of the magnetic field as created by that. So they would be coming out of the plane on the right side and into the plane on the left side. So it would be curling around in this direction. So that means that the field on the right side of this long parallel wire would be coming out of the plane. Now for the circular loop, it's a little bit of a different rule. Now I tried to find a picture that would show you this using the same sort of right-hand rule. So here it is. If you have a if you grab the wire so that your thumb points in the direction of the current. However, in my diagram, my current is going counterclockwise, but in reality in this problem it's going clockwise. So really, if you were to grab this so that the current was going the other direction clockwise, you would find that your fingers would rather than in this picture curl out of the middle of the loop, but they would actually curl in. So the magnetic field for wire 2 will be going in here, and also in here, and in here. So in the center of this loop, the field line will be going into the plane of the page, and so we would say that B2 is going in this downward direction, down through the plane. There's a variety of right-hand rules. So this one is continuously using the thumb being the direction of the current and the fingers representing the field. But you can use a different version if you wish, if it makes it easier. So when you're dealing with a circular wire or a solenoid, you can use a different form of this right-hand rule. Instead of your thumb representing the current, make your thumb represent the field, and then your fingers curl in the direction of the current. So interchange your finger and your thumb rolls, and you'll find that if you point your fingers and curl them around, because it's easy to do with a circular coil, in the direction that's shown, you'll see that your thumb will point downwards. Now that thumb will be pointing the direction of the field that is induced only in the center of the loop. On the outside, it would be going in the opposite direction. So this is just a different version just to show you. Well, anyhow, we need to find the net magnetic field. So the net magnetic field will be equal to the difference between these two magnetic fields. So B1 minus B2. And I'm going to have to take the difference between what, because one's going up and the other one is going straight down, out and into the plane of the screen. The expression for both of them are not the same. Now, for number 1 wire that's a long straight conducting wire, we use the expression of mu naught I all over 2 pi r, and r would represent the distance from this wire to where C is. However, for the circular wire we have a different one. If you turn back to your notes, you'll see this formula. It's not part of the AP exam. So we have B equals N times mu naught I all over 2R, and R represents the radius of the loop. N would be if you have more than one loop. And there's that picture I was showing you. So you could choose to have your fingers represent the current, and the thumb would be the direction of the B inside the loop. Anyway, we need to use this expression for B2. So there we go, and then in this case, N will be equal to 1 loop, because I think we only have a single loop here. So B1 will be mu naught I all over 2 pi r, and b2 will be just mu naught I, and just divided by 2r. And now you can substitute in and get your answer. And there's the substitution, and you can do some cancellations. And after putting it into your calculator, you should get an answer of 1.14 times 10 to the power of negative 5 Teslas. And since the answer comes out to be positive, that means that's in the same direction as B1, which means it is directed upwards, perpendicular to the plane of the page as listed below. And that's it for this example.